Okay, so I want to, for the rest of the course now, so the plan is that we're going to finish the session today, like by 12:15 as scheduled. And then we're going to have probably just like one session in the afternoon. We might have a little bit of a longer session. We started 1:30. We might go like for 2 hours, but then we finish there, okay? So instead of having the 2 sessions with the break, so it might be a little too long, but then you guys go home earlier, right? Okay, so the topic that I wanted to discuss, right, for this last part of the course is the following. Right? So far, right, we have mostly, I mean, essentially what we have seen from day one was the idea of using random sampling to generate scenarios for this problem, right? So that is a complicated, right? This is a problem where we cannot evaluate the functions exactly, right? We've talked about that many times. So we've discussed, all these asymptotic results, how, convergence when you do random sampling. Then, like Güzin discussed all these methods to assess the quality of the solution, right? When you have finite sample, when you're dealing with only finite sample. So, but all that is still based on the idea that you're doing random sampling behind, right? Well, so we can do a lot of that, but sometimes it's not the best choice. So there are other ways that one can do it, right? Güzin also mentioned talk about the quasi-Monte Carlo methods, which one can think of that as being a non-random method, right? Because those are methods in which you're choosing the points, right? But there's yet another class of problems that we're going to discuss today. That the idea is, you try to somehow get some information about the problem in order to choose the scenarios. Right? So the one criticism one makes about random sampling is that, well, you're not really looking at any information about the problem, right? When you're just trying to do sampling from the distribution, it doesn't matter what the objective function is, you're still going to sample the same thing, right? It's not affecting your sampling. Or another issue is that, well, if you have some kind of a risk function, right? We discussed, for example, about the SVAN, right, earlier on. And where, SVAN essentially looks at the tails of a function, and one can think, it's not unreasonable to think, right, that if you're trying to do, say, minimize the SVAN of a function, you may not want to, you may want your scenarios kind of concentrated on the tail, right? You may not want your scenarios just spread out, just like when you estimate expected values. But random sampling, it just samples over the distribution. It's not taking into account any characteristics of the problem, right? And another thing here that we're gonna see this a bit later is that turns out you cannot just do SAA when you have the case of multi-stage problems, because then we're gonna talk about that to see why this can be a problem. Right? So if multi-stage is a problem, has its own characteristics, right? Although in an abstract way it's still the same problem, right? We can still think of we are minimizing some expected value of a function, right, of C, but this function is the optimal value of the cost from second stage on, right? You guys have seen that in your stochastic optimization course. But the fact that this is the optimal value of a dynamic problem changes a lot, okay, in terms of the scenario generation. Right? We're going to see why, right? Why this is a problem, okay? So what's the idea? So there's a big effort, right, a research effort in this area, which what is behind that idea is this idea of stability, right? So that's a type of result that is behind much of what people have been doing in this area of scenario generation. So many people, particularly people like Georg Flug and Werner Romisch, Dupacheva, who already passed away. There's a lot of effort, particularly in those groups, to develop this type of methods for scenario generation. They are all based on this stability approach. It's important to understand well what this stability approach means. Okay? So what is the idea, right? So imagine that you have the distribution of the P is a distribution, right? And this C takes values in some set, right? Think of this could be a subset of K, right? It's a multidimensional random variable. Now, imagine now that I define the optimal value of my problem as the optimal, right, as a function of the distribution, right? I'm just parameterizing the problem in terms of the distribution of the random variables. Okay? So I have a V of P, and let's define this set here, which is, well, the idea this X rho is just taking X intersect with a ball of size rho, right? So that's the idea is just, we're going to see in a second why we need this, but it's just that you don't go, you sort of look at limited versions of X, right? Of course, as you grow rho, I mean, this you end up covering the whole X probably, right? But here you guarantee that things are bounded, right? Okay, so now, let's define this distance, okay, between two distributions. Imagine we have two distributions P and Q, right? So I have, think of Q being the distribution of another random variable xi tilde, right? And I want to measure the distance between these distributions, okay, between P and Q. So one distance that can be defined is the following, right? And that's the nice thing about this distance, because it's a distance that is defined in terms of subjective function of the problem. Okay, that's the interesting thing about this approach, right? And what makes it valuable for this class of problems, right? Because we are looking at a distance that is based on the objective function, right? So we are taking, what is this, right? We are taking the maximum value, right, the supremum, over the difference of G for the same X, right? G, the expected value of G with the expected value with respect to the P distribution, and the expected value with respect to the Q distribution, right? So essentially say, okay, calculate the average value of this under the two distributions, right? Take the difference and take the maximum over X, right? This is going to be a distance for me, a distance between P and Q. Is it clear, right? How we are calculating this, right? I mean, don't tell me how to calculate this in practice, right? I mean, so far we are still in the, at a kind of conceptual level, okay? But still, one can define this distance, right? For any rho, right? We can still define this, okay? So that's what I'm going to write this as G, D of G and rho, right? Because it depends on the G and depends on the rho, okay? Okay, so now we have this distance. So here's the main result, right? That can be shown is that turns out, right, so it's possible to show there exists constants rho and epsilon, okay, such that we guarantee that as long as the P and Q are not too far, right, as long as they are not more than epsilon away, then the difference in optimal values is bounded by the distance between the distributions. Right? So it's important to understand why. So you can think of this as some kind of, that's why this is a stability result, right? You can say, well, if I don't perturb my distribution by too much, right? If P is less, the distance between P and Q is not too big, then my optimal values are not going to, I won't be much difference in the optimal values either, right? It's essentially a stability result. And you can see where this comes from, right? Because, I mean, that's why the distance is defined this way. Because if this is the difference between expected values, right? We want, after all, to minimize the expected value. And you're essentially saying that, well, the difference, the maximum difference between the expected values is less than epsilon. So if you want to minimize, yeah, it wouldn't be much difference either, right? The difference of the minimum shouldn't be too much, right? Because essentially this is saying that the two problems are close enough, right? Uniformly, because, right, this is a supremum here, right? So that's kind of the idea, saying, okay, they are reasonably close, then the optimal values should be close, okay? So that's the main idea behind this type of approach, right? So to say, okay, ultimately what we want to guarantee, right? P is the original distribution. Well, we know we cannot calculate this, but maybe I can calculate with Q. That's the hope, right? You want to choose a Q, and maybe it's easier to calculate the expected value with Q than with P. Maybe Q has much fewer scenarios, for example, right? You know, P could be a distribution with, thousands and thousands, or 10 to power 10 scenarios, right? I mean, this could be an uncomputable thing, but this is could be a much smaller version, right? So for example, much fewer scenarios, and then, well, if I can still guarantee that the optimal values are close, that's perfect, right? That's what we want to do. Okay, so the difficulty here, so this is nice as long as we can calculate this, of course, right? If you cannot. So that's the comment, right? That they'll be close. But yeah, here's the comment, right? So calculating this distance seems even harder than the original problem, right? So that doesn't make sense to try to do this exactly. But if I can find a distance that bounds the G, that's good, right? So if you're able to bound this dg distance, and you guarantee that this one is small, that's good too, right? It's an upper bound. If this is small, this is going to be small, and then everything else is going to be small, right? So we're good, right? So the problem is just to find something that we can guarantee that bounds the dg for any p and q, okay? So which one? This one? Oh, no, I'm just saying, if I can find some d, I'm not telling you, huh? No, I don't have that. If I can find one that guarantees it, my point here is that if I can find one with this property, right, and then if I show that the dp is small, then dg is going to be small, right, because it's an upper bound. But yeah, I haven't shown what the d is. It's not even clear if it exists, right? It's just at right now. So that's what we want to find an upper bound for the dg. As long as we have an upper bound, you're happy, okay? Okay, so let's consider the problem of measuring distance between probability distributions is a well-known problem, okay? So a lot of people, there's a lot of work on that, even people basically in probability theory, right? Nothing to do with optimization, right? There are people developing many different types of ways of measuring the distance between distributions. I mean, it's a classical problem that goes back centuries, okay? So here's one class of distances. There's a very large class, as we'll see in a second, right, which is defined as the following, right? So one can define the distance between p and q as the maximum over some class of functions of the integral of h with respect to p minus the integral with respect to q. You can think of this as just being, right, the expected value of h, right? H, now think of h being a random variable, right? Now there is no optimization going on, right? So it's just the expected value of p minus the expected value of q. Right? You can think of this way. And then I take the maximum over all functions in that class, right? So for example, if I take h, right, this class h to be any function, any bounded function, right? That's one possibility, right? Take h being any function that you want, well, bounded, right? And bounded and measurable, okay? So it turns out that one can write this as just this distance becomes just the supremum, right, of the difference between p minus qa for any possible set, any measurable set. Okay, so that's what we would get here, right? So if you take h being all these functions, this is right is the maximum value of p minus q for any set. Okay, that's too much though, right? That's too fine for our purposes. Do you agree? Right? Why is that? Right? Because, for example, one of our goals could be, for example, to go from a continuous set, a continuous distribution, to a discrete distribution. Right? You want to select scenarios, after all. Right? So if that's the case, think about it. Right? If you're trying to approximate a continuous distribution with a discrete distribution, this distance is not going to work. Right? Because if you take the continuous set here, it's got to be the same set. Right? So the difference between P and A and Q of A, right, if you take finitely many points, this one is going to be 0, and this one is going to be whatever, right, the discrete distribution over that set. So this difference is always going to be 1, right? Okay? So this wouldn't work. For our purpose, that distance doesn't work. It's too fine. Okay, so we need something else. This, by the way, is called the variational distance. Right? It's useful for other purposes, but not for what we want, right? Which is to approximate a continuous, like a continuous distribution with a discrete distribution, right? Or a distribution with a very large number of scenarios with one with a smaller number of scenarios. So another type of class of functions that it can be used is the bounded functions, bounded Lipschitz functions with a Lipschitz constant 1, right? So functions that satisfy this, right? H minus t is less than or equal to the distance between s and t, right? For all s and t. So that's another class. A more useful class is one that is equal to this one, but then you drop the boundedness assumption, right? So you just look with Lipschitz functions with Lipschitz constant 1. The functions could be unbounded, okay? So it actually turns out there's what's called the Kantorovich distance. And so we can say, right, this is going to be the supremum, right, over all functions that have this property, right, even if they are unbounded, right? The supremum over this difference over all functions satisfying this, okay? Well, it turns out it's not difficult to see that on the real line, you can't, it's hard to compute this distance, right? Because we still have a supremum over a set of functions, right? It's still, I mean, we are still at the conceptual level, right? But in the real line, on the real line at least, this turns out to be much easier, right? On the real line, it turns out that the Kantorovich distance, we can think of this as simply this integral of the difference between the cumulative functions, right? So if you draw a picture, we see that, right? So here is, say, f, and this is, I don't know, maybe this is g. Let me draw another color, right? Imagine that we have these two functions, right? The white one and the red one. So this is essentially measuring the integral of f minus p, right? So for every value here of z, right, we measure what's the difference between the two functions and take the integral of all this, right? Okay? So that's essentially, you can think of this as being the vertical distance, right? But turns out this is also the same as looking the interval of f minus 1, right? If you look at if you draw the inverse function, right? If you invert this graph, right? It's almost like looking at the horizontal distance here, right? What's the difference in this way, right? You can see why it's the same, right? Because you're measuring like in the horizontal way, right? So it's the same. You can look at the graph, either way, or you can twist like 90 degrees. It's going to be the same quantity. So that's why we get this, right? Which then, this is certainly computable, right? This is much more palpable, right? I mean, okay, and this is the CDF of the function. So this is quite used in practice, right? This is also goes by the name of Wasserstein distance, in case you have heard that. But Wasserstein there's a bit of a generalization that we'll see soon. Okay. And finally, there is another class that helpful are the Lipschitz functions of order Q, right? With Lipschitz constant 1. What it means to be a Lipschitz function of order Q is this, right? That the difference between the functions is bounded by the norm times the maximum between these quantities, the maximum of 1, the norm of S to Q minus 1, then the norm of T to Q minus 1. Okay? Well, let's think for a moment. Why would one possibly want something like this, right? Why could we possibly gain by looking at a function with this class? I mean, clearly this is a bit more general than the previous one, right? This one was imposing, right? This one was imposed 1, right, for this multiplier. But here we are allowing a bit of flexibility, multiplying this by the norm of S and T. But why? Why could we possibly gain by this? Any idea?
We can analyze, for example, extreme events. We can analyze extreme events.
Why?
Because we're taking the maximum between norms.
Yes. Extreme event, but event. I mean, we are still thinking of functions here, right? But no, I know what you're getting to, right? But in terms of the functions, right? What are we gaining by this generalization? Can you think of a situation? Right? Let's say order 2, Lipschitz of order 2, right? Lipschitz of order 2, we essentially are multiplying, we are saying h minus t, hs minus ht has to be less than the norm, right, of s minus t, times the maximum between 1, norm of s, norm of t, right? That would be a Lipschitz order 2. So what do we gain by allowing the norm to be multiplied by the norm of s and the norm of t? Felipe? Right. This allows more functions. For example, it could be a function that increases, right? Like this, right? Going more and more, right? Because remember, we are talking about unbounded functions here. There is no restriction that the functions are bounded, right? And the space here, the space where this S and T's lie, this could be an infinite space, right? We're not saying that this space is bounded, right? So this function could just keep growing. So if you try to impose that is the previous condition, that the function has to be Lipschitz, maybe it will not work, right? Because it would work if you would restrict yourself to some kind of compact set. But if you try to impose this for any S and T in your space, right? In this case, it would be the space of scenarios, right? Just think of you have a continuous distribution, a normal distribution, for example, right? A normal distribution has no bound, right? You can have any value. So then, right, if you try to impose this, it might be too much, right? Even for a function like like a piecewise linear function, right, as it often shows up in optimization, right? If it's a piecewise linear function, but if it has no bound, this just keeps growing and growing and growing, right? And then still you cannot get a Lipschitz constant, right? So by doing this, we are allowing a bit more generality, right? We can say, okay, maybe it can grow quadratically, right? I don't know. You know, I can not just S minus T, but I allow this multiplied by the norm, right? So when S is very large, I take that into account. Okay, so that's the idea. You allow more functions, okay? And this is what leads to what's called the Forte-Mourier distance between two distributions, okay? So that's another one that's helpful in practice. Okay, so now let's consider yet another set, right, which we're going to call HC. And those will be the functions that are sort of like a Lipschitz function, okay? Except that instead of having S, the norm of S minus T, we are going to change this by some kind of quote-unquote distance function between scenarios, right? Because that's what the Lipschitz one was doing this, right? We're saying HS minus HT is less than, right, in absolute value, is less than S minus T. This will be the standard Lipschitz, right, of order 1, of constant 1. But here saying, well, instead of looking with S minus T, I want to be a bit more general and maybe work with some function that measures, it doesn't have to be an actual distance, okay? It's just something that has, of course, properties that resembles a distance, but doesn't have to be a distance per se, right? For example, a function that has this property, right? That, you know, it's, if the function is 0, then they are the same, or, you know, it's symmetric. Here you can think of it as some sort of continuity, right? So if the norm of S minus T goes to 0, the CST goes to 0. So those are reasonable things to have, right? Properties to have. And this is an important one, right? So this is saying that turns out that the triangle inequality is really important for this type of results, right? That we're going to see. So here we are saying, well, maybe C does not have a triangle property per se, right? The norm has the triangle property, of course, right? The norm of S minus T is less than the norm of S plus norm of T. But we want to have something like that for the C function, right? And the C function, so the idea here is that C has this property, right? CST is less than lambda S plus lambda T for some lambda function, okay? Which is bounded on bounded sets. So this is just to ensure that we have some kind of triangle inequality going on. So there again, why are we allowing for this generalization? Well, because it turns out sometimes it's nice to play with the C function, right? To twist the problem the way we want, okay? In fact, Wellington has a paper with Claudia and some other collaborators where they look at a particular type of function that includes the variance of these distributions, which is nice. This is a way to get the extreme events that he was talking about, okay? So then it gives you another freedom, right? Another degree of freedom for the problem, right? When you can play with this function C as well. You can define your own function if you like. You don't have to work with the norm, okay? Okay, so now let's go back to our optimization problem, right? So we saw a number of distances, right? Possible ways to define distance between distributions. And now let's suppose that our function has this property here, right? This is our objective function. So now you can think of G, for example, being a function of, for example, the result of a two-stage problem, right? A two-stage stochastic programming problem, right? Well, we know that a two-stage problem, well, right? So imagine that we can enforce that GS minus GT has some kind of sort of a Lipschitz property on S and T, but I'm allowing this to depend on X, right? Again, because if you don't this, it might be too strict, but I allow, in a sense, I'm allowing the constant here to change with X, okay? So many problems, I mean, if you think about, for example, in the two-stage case, right, the value function of a two-stage problem is piecewise linear, right? It's convex and piecewise linear. So in both, right? I mean, if the randomness, for example, is only on the right-hand side, right? It's a piecewise linear function in C, right? If you have your G function, right, is the second stage, right? It's like at the minimum of some problem like this, right? Wi equal to H, right? C minus Tx, if you have something like this, right? Well, we know that this is going to be piecewise linear in H, right? So then we automatically get this type of a Lipschitz property, right? So that's an assumption that, holds for many problems, not for all problems, but it holds for many problems, okay? So then we can say that, well, if you have this, right, then you can say that the dg, I can write this, right? This I take remember, rho was that quantity. Remember, we are taking the supremum. We can take the supremum of x rho. What's x rho, right? Is the x intersect with the ball of size rho, right? So why is this inequality? Any idea why we can write this? Right? Remember, this is our dg function, right? The dg function was just the supremum of the expected values, right? This was the first distance function we discussed, right? The one for which we could show stability, right? So remember that dg function was the supremum of the expected values, of the difference between the expected values. But now we are saying that this is less than the supremum for the h's in this class HC, right, that we discussed, which is all functions that are sort of C Lipschitz, so to speak, right? So it's not exactly a Lipschitz, but it's a C Lipschitz. So why do we have this inequality? Here is the supremum over X, here is the supremum over H, right? So why is this? Any idea why this holds? Right, so this was just can think of this, for simplicity, think of the S now being, the C function being just the norm of S minus T, okay? Just to make it simpler, okay? So if this is less than S, think of this as being just the norm of S minus T, right? So this is the class HC, right? All functions that are Lipschitz, right? For practical purposes. So how come I can choose the supreme over X for a supreme over H of the Lipschitz functions? Why is that? Felipe?
I think that when you divide G by you have a function that belongs to this class, HC. And then when you move the X code set, you are changing this function. So, but all for each X the function G divided by
belongs to H, right? Because it has this property, right? So if you think about, if I X rho, that's important to take X rho, because X rho is the intersect of X with a ball of size rho, right? So we know, because this is a non-decreasing function, this is always less than or equal to phi of rho, right? So I can bound this whole thing by phi of rho times CST, right? So if I divide by phi rho, that's Felipe's argument, right? If I divide this by phi rho, essentially the consequence of this, right? If we divide by phi rho, is that 1 over phi rho times G, right? So this function belongs to the class, right? For a fixed X, right? For a fixed X, this function here is in the class HC. Right? Well, well, but this for fixed x, so this is one particular function. But so taking the supremum over all x's is a particular casing of taking the supremum over all functions in HC, right? It's a subclass, right? So the functions that have this form, right? If I take the supremum over x in whatever set of these functions, still this has to be less than the supremum over all possible functions in HC, because each gx is in HC. Is it clear? Right? So this is a subclass, right? We can think of this as being a subclass of all functions in HC, so that's why you have this inequality. Okay? And this is our distance dc that we had defined before, right, in the previous slide. So now we can see we're starting to connect these two things, right? The distance that came just from the objective function of the problem with a general distance, right? So we can say from this inequality, you can say that dg rho is less than phi rho times dc. So it's a little better than what you had before, but still not good, right? Not fully good, because it's still calculating dc seems hard in general, right? Because you still have the supremum over a set of functions. So it's still not what we want, but a little better, right? So now all we have to do is bound this dc guy. And then if you can do that, right, bound by something we can actually calculate, right? The bound is here, the bound is valid, but still we cannot calculate this because it depends on the supremum. We got rid of the dependence on the objective function of the problem, but still we have the supremum over all functions that have this property here, right? Which still, how do we solve that? This is a functional problem, right? That's too hard. But let's see what else we can do about that, right? So calculating still seems pretty difficult. So let's make a little detour here and talk about a transportation problem, right? And we'll see in a second why the detour, okay? So it turns out that this French mathematician, right, Gaspard Monge, right, the famous mathematician, back in the 18th century, he proposed this problem, right? He said, it's a seemingly very simple problem, right? He's saying, okay, how can I transport soil, right, from site S to site S prime with minimum cost, right? So imagine that you have two sites here, okay? You have your site S, and then you have a site S prime, I don't know, maybe it's a square, right? So you want to transport your sand here to here, okay? To transport everything here to here at a minimum cost. So Monge was saying, okay, suppose I know the cost of moving one grain, right, from one location here, S, to one location, S prime, right? Imagine that we have a cost, right, to move a grain of sand from here to here. So if I have, and I measure this cost by some function C, right, S prime. Is it clear what the problem is, right? So if I know the cost for every grain here, right? And every position here, I know the cost of moving from one position here to one position here, it's natural to think, okay, what's the cheapest way? Okay, what's the cheapest way of moving the sand to get everything that I had here into the square? Okay, is it clear? Of course, I mean, those things have to have the same volume, right? You cannot have less volume here, otherwise you have too much sand, and then in this one cannot have less volume than this, otherwise, well, you have to fill it. How can you fill where the sand comes from, right? So they have to have the same volume, right? You move all sand from here to this place. Right? So it's a apparently simple problem, but turns out to be really hard, right? Really hard, right? And why? So let's see, how can you think of this problem in mathematical terms, right? So one way of defining, in fact, that's how people initially look at this problem, was the following. I say, okay, suppose I have a finite measure here on this set, right? And nu is a finite measure here, right? And let's assume they are equal to 1, right? There's no loss of generality, because we know they have to be the same mass, total mass, right? So we can make it 1, right? Okay. So essentially what we want, right, is to find a mapping, right, from S to S prime that has this property, right? So the measure of anything here has to be equal to the measure on the origin, right? Because we have to preserve volumes, right? So if I look at the image of this set, right, I need to have the same volume here as here for any subset. Okay, so it's kind of natural, right? Again, this is the reason that we cannot, fabricate, manufacture sand, or we cannot lose sand, right? So this has to hold for any measurable set, right? And of course, we want to minimize the total cost, right? We want to minimize the cost of transporting C, right, with the cost of moving from S to TS, right? So we're essentially finding a mapping saying, well, my S prime here is going to be a T of S, right? So I want to find among all possible mappings, what is the one that gives me the least cost, right? So is it clear that this is right? Mathematically, that's the problem that Monge had proposed, right? I want to find what is the optimal T. Well, what is hard about this problem? If you had to solve this, right? Why is it hard? Suppose, right, you had to do this, right? Solve this problem, find the optimal T. So, yeah, first we're not even clear if there exists a T. How do we know, right? Maybe there is no T. In fact, I mean, this showing existence was the first step here, and it took, decades just so someone was able even to show existence of the T under proper and proper conditions. So even if showing existence is hard, let alone optimizing it, right? And if you think about this, what is the feasible set of this problem here? Right? It's the set of what? It's the set of all mappings, right, that have this property here, right? So first, yeah, we don't even know if that set is empty or not. And even if it's not, I mean, that set, it's non-convex for sure. Okay? It can be shown that it's non-convex. So this is an extremely hard problem, right? A problem for which you cannot, and in fact, this eluded mathematicians for more than 150 years, right? No one, there was someone who, like in the 19th century, did some advances, showed some conditions. I mean, the person even won a prize, but it was not very satisfactory, the answer, right? And because the problem itself, in a sense, is not very well posed. Right? It's a too difficult problem. Right? So yeah, so existence, and then you have this optimization problem. Of course, is an infinite dimensional problem, right? Potentially, and feasibility is non-convex. Well, that's way too hard, right? Even if it's finite, right? If you talk about finitely many points here, still, it's the number of the space of functions is, it's a functional problem. So too difficult. So, but here's the breakthrough, right, on this problem. So then in 1942, then this Russian mathematician, like the Leonid Kantorovich, well, he actually did some work. He was not even aware of Monge's problem. He just was working on something else, but he proposed something that turns out to be a solution for Monge's problem, right? So what did he do, right? So Kantorovich's solution, you can view. Imagine that we relax the assumption that T is a function, right? Because the part of the problem here is that we are imposing that we need to take any point here to one point here. But this has to be a function, so we cannot break this into two, right? So each grain of sand here is indivisible, right? Because you cannot take one grain here, it's sent to two parts, right? So if you have one grain, it has to go to one grain here. So that's why it's constrained this problem, because you're saying, okay, there is some atom there that you cannot really split. Right? Well, what Kantorovich did was essentially say, no, I'm going to forget about this. Right? Again, he didn't know about Monge's problem, but it turns out that's what his problem is about. Right? He was thinking of something different. He was thinking like, well, I want to move things from here to here, but not grain by grain, but in terms of masses. Right? So his goal is to think, okay, how can I move a mass from here to here, which doesn't have to be one individual grain. Right? We can think of this as being infinitesimal. When you talk about masses here, you can doing something that is infinitesimal. So instead, what we get here, so in Kantorovich problem, what one gets is you can identify, right, this transportation plan. Instead of having a transportation map, now we call this a transportation plan, right? So you can identify this with the space of product measures on the space xy, right? Well, I should write S prime, sorry. This is a product space on the space, right? We are looking at measures on the product space S and S prime. So essentially we are saying that you can think of this, right? So pi AB, right, is how much you move from set A to set B, essentially. Okay? So it's like we can think of this as a continuous, an infinitesimal version of Monge's problem, right? Because we are moving entire masses now. So how do we impose the constraint, the volume preserving thing? Well, the product, right, the measure of A and, well, again, I should have written A and S and S prime. Sorry, so let me write again what this property is that pi AS, sorry, instead of Y, it should be an S, right? This should be mu of A, right? And the pi of S, pi AS prime, and pi SB should be equal to nu of B, right? So this is essentially saying, well, the probability of moving from A to the whole space, that's the measure of A, right? Because you're moving this mass from here to the, how much you move from A to the whole space, well, that's the volume of A. And likewise, and vice versa, right? The amount you move from S to B, if you take the whole space here to B, then that'll be just the measure of B, right? So you're associating probability distributions, right? Which, infinitesimally you can think of this, right? How much I'm moving from this to that, from X to a point here to a point here, but now we are allowing these points to be divisible, okay? So we can formulate Kantorovich problem in this way, right? You can say, okay, now Kantorovich problem, you're trying to minimize over all probability measures on the product space, right? The integral of CST times the marginal, times the pi function, okay? And what is the constraint is that pi must have marginals mu and nu in the sense of this, right? So the pi, the probability distribution of A times the whole space is mu of A, and pi of the whole space times B is just the nu of B. So, and that's a problem that is much better than the previous one, right? If you think about it, what type of problem is this? Now, the variables now are pi, right? So what kind of structure does this problem have? What do you think? The variable here is pi, right? So you're looking at this over all probability distributions, right? So what kind of structure is it? Let's think of the objective function, right? The objective function is the integral of c times pi. So if it's just c times pi, this is what? It's linear in pi, right? So this is just a linear optimization problem. It's still, pi could be, in principle, pi could be an infinite dimensional distribution, right? So we are talking, but it's a linear optimization problem, but potentially an infinite dimensional problem, but it's linear optimization. So this is far, far better, right, than the previous problem, which we couldn't even show existence, right? And it was also non-convex. So this one, okay, it's an infinite dimensional problem, yeah, but linear optimization is extremely well developed, even in infinite dimensions. There's the whole thing, right? The whole theory of duality, algorithms, all that is developed even for infinite dimensional space, right? So And it's a convex set also, right? Because the set of all probability measures, well, that's a convex set, right? So this is a much, much, much well-behaved problem, right? And that was gained simply by relaxing that assumption that, you have to move 1 grain to 1 grain, right? It's just by being more flexible, allowing, infinite divisibility, we get a problem that is actually much easier to solve. So there's duality, algorithms, and so on, right? And so now in the literature, this is called the Monge-Kantorovich transportation problem, right? There's like entire books written just about this problem. Because, right, Monge was the original contributor, but Kantorovich essentially gave the solution to the problem, right? So for example, right, here's a concrete case, something palpable, right, that we can handle. So imagine that we are in the case of finite sets, right? Suppose that my set S has finitely many points, right? So I can think of mu being the probability of each point, right? Think of this as a distribution, right? Remember, mu is a distribution, right? So it's a distribution with n points, and I have nu is a distribution with m points, right? 2 sets. So this is the support of each distribution, right? So this Monge-Kantorovich problem can just be written this way, right? Instead of what was an integral of c times pi, becomes just the sum, right, of c for every scenario in S and every scenario in S prime times the Pij. Now we have just a vector, right? A matrix Pij, right? That calculating the probability of any point in S to any point in S prime. And the constraints are really easy, right? The constraints, remember the constraints that like pi has marginals mu and nu. Well, that constraint now is simply saying that, well, if you sum for all i's, right? If you sum the Pij's for all I, that's equal to mu I. If you sum over j, that's equal to, if you sum over I, that has to be equal to nu j. So this is a very simple LP, right? Linear program, right? It's a linear program. This is finite dimensional. A very simple constraint set, if you think about, right? So this one is a very easy problem to solve. Okay, you can even develop specialized algorithms. But it's a linear program, and even more, it's a very well-structured linear program. Okay? So just before we go to that, so just how to finish this part here and how this integrates with the rest, right? So if you write, I'm going to skip this one, but if you just write the Monge-Kantorovich problem, instead of writing the marginals, if you write the difference of them, right? This you have an equivalent problem. But the problem, and it's called the Kantorovich-Rubinstein, but turns out that this leads to this dual. The dual of this problem has this form here, right? This Kantorovich is equivalent to the Monge-Kantorovich. And the dual of that problem, but this is also linear, it's also a linear optimization problem, and has this dual, right? The dual of that problem is the supremum over h of h times sigma, and sigma here is the difference, is the measure given by the difference, right? So I can think of the objective function as being the supremum over hs times mu s minus the integral of hs nu s, okay? Or ds here, should put a ds, right? So this is the objective function, subject to the constraint that hs minus ht is less than cst, okay? And c, remember, c is the cost, right? Transforming. So, have you seen this problem before? Yes, right? Where? Huh? A few slides before, right? long ago, right? Right? Remember, what was this problem? This was exactly the Kantorovich, what we had called the Kantorovich distance, right? Which was, remember, we said this Kantorovich distance was the supremum over the difference of expected values for all Lipschitz functions, right? With that h function being just the Lipschitz of order 1, right? This was exactly what we call the Kantorovich problem. So what we are saying here, now you see that's no accident, right? That distance was called the Kantorovich distance, right? It's coming from here. So what can we say, right? So the dual of this problem, right? The dual of the Monge-Kantorovich problem is this, right? So what can we say about the relationship, right? So remember, the Monte-Kantorovich is the optimal value of this problem. So what can we say about the optimal value of this problem compared to the with the optimal value of this problem? If one is the dual of the other, right? There's a bound, right? That's weak duality. Says that this one is always, let's see, if you're maximizing, yeah, this one is always less than or equal to the value of this one, right? So that's what we get here, right, by weak duality. So if you call that, let's call DMQ, the distance between P and Q based on the Monte-Kantorovich problem, right, that linear optimization. So by weak duality, we have this. And, well, there are some conditions that, you know, on C, for example, if C continues or if it has lower semi-continuous in triangle inequality, you have no duality gap. So in conclusion, what we get, right? If we put everything together, remember we had this inequality, right? So this is our originally D0. Now we know that this is less than DC. And now we are saying that DC is less than the optimal value of the Monte-Kantorovich problem, which is now is something we can calculate, right? Because this is a linear optimization problem. So now we have finally a problem, a way of calculating distance between distributions, just solving this linear optimization problem. And we know that will give a bound on this whole thing, right? Even on the DG. Okay? So that's essentially how this whole thing, how this all it is tied up, right? Through the Monte-Kantorovich problem. So we have a bound. So in particular, this particular case, this is called the Wasserstein distance over eta. We can take this is a particular C function, right? And you get the Wasserstein distance. And so now, for example, if you want, all we need to do is try to minimize the distance Monte-Kantorovich between P and Q, right? That's all we need to minimize this, right? And if you minimize this, you minimize everything else. So minimizing this now means, for example, if I can try to find the support, I have a P, my original P. I want to find a subset of the support of P that contains, that minimizes that function, okay? So after lunch, we're going to discuss about this particular problem, right? How do we go about then selecting scenarios such a way that makes this distance small, right? Because now we know we can forget about all these other distances that we looked at. Our goal is simply now to minimize the Monte-Kantorovich distance, right? Choose Q in such a way that this distance is somehow minimized, okay? So that's what we're going to do after lunch. All right?
We start at 1:30?
Yeah, well, we can start a little bit later if it's better, you know, to give people lunchtime. And since we started a little bit later, right, in the morning. Is it 15 minutes later, maybe? Like 1:45? Is that okay? Yeah, it's better. So you guys have time to get lunch. And okay, so we come back at 1:45. Okay?